Okay, so we left off here around 7.7, which deals with E2 regioselectivity. So we've talked about SN2 reactions, so substitution, nucleophilic, it's second order. Then we moved on to E2. We said if your substrate is methyl or primary, SN2 works well. If it's secondary, kind of works, not so great. But if you have a tertiary substrate, then you will not get any substitution. You will only get elimination in those cases. So if we take a look at this substrate here, so this would be 2-bromo 2-methylbutane. Well, we know that this carbon here is the alpha carbon, and then we have two types of beta carbons, right? We have a methyl group here and a methyl group here. Those are chemically equivalent. And then we also have a methylene here. So we have the blue types of carbons and the black type of carbon, right? So those are the two types of beta carbons. So what I'm going to do is I'm going to highlight one of the blue protons, okay? So that's one type of beta proton we have. Maybe I'll put it, instead of there, maybe I'll put it here on this one, okay? And the other one is one of these ones here, okay? Give me a thumbs up if you understand that there's two different types of beta protons. I mean, there's a total of 8 different protons, but there's two types. Okay, cool. So now that we have that, there's two possibilities. We have sodium ethoxide. Now, ethoxide, O minus, that's a good nucleophile, but you're not going to react a tertiary alkyl halide with ethoxide as a nucleophile. The ethoxide is going to behave as a base because it's too sterically hindered for it to attack here. That's too sterically hindered, but it can pluck one of these protons off of the periphery. If it was to take off the blue proton, okay, if it pulled off the blue proton, you would end up with this product, okay? So if I complete the mechanism, right, you would make the pi bond, you'd lose the leaving group, and you'd end up with the compound in the blue box, okay? If it was to pull off the black proton, so let me just erase this, okay? If it pulled off the black proton, then you would form a pi bond here and lose your leaving group, and you would end up with this compound, okay? So give me a thumbs up if you see these two different alkenes that could be formed from the abstraction of the two different types of protons. Are you with me on that idea? And if you're not, don't hesitate to stop me, okay? So two types of protons. The blue ones would reveal or would produce the product in the blue box. The black ones would give you the product in the black box, right? Two different types of protons that we could remove here in our E2 reactions. Well, if we look at those two, the more substituted alkene, okay? So the more substituted alkene, we call that the Zaitsev product, alkene, and the less substituted product, the less substituted alkene, we call that the Hofmann product. So if you're unsure about the substitution, look at the two carbons in the double bond of the Zaitsev product. They're attached to a total of 1, 2, 3 carbons. If you look at the carbons in the blue product, they're attached to a total of 1, 2. So 3 is a bigger number than 2. And so the Zaitsev is the more substituted product, and therefore it is the more stable product. It turns out that in this case, you actually get mostly the Zaitsev product, which is the most stable product. So let's review. At the bottom, it says when ethoxide, right? With ethoxide, which is this, is used as your base. 2-methyl-2-bromobutane gives 2E2 products, with the major product being the more stable alkene. We call that the Zaitsev product, produced as the major product. The less substituted alkene, the Hofmann product, is the minor product in this specific case. So we say that E2 elimination is a regioselective reaction, right? It's selective for the blue region. It selected the blue proton more than it selected the black proton. So we say it is selective by a region, right? The blue proton is in one region of the molecule, the black proton is in another region, and it's more selective for abstracting the black proton than the blue proton. So that's what regioselectivity means. And it turns out that regioselectivity can, as a matter of fact, be controlled by choosing the strong base, okay? So when ethoxide is used, it turns out that we get mostly the Zaitsev product. However, if we use a bigger and bulkier base, it's actually going to produce mostly the Hoffman product. So let's take a look at that. So this is some data that is summarized in a table here. This is our substrate, our 2-bromo-2-methylbutane. Here's the Zaitsev, here's the Hoffman, and these are their distributions. When we use ethoxide as our base, we say that ethoxide is an unhindered base. Okay, even if you just draw the structure of ethoxide, right, you can see that the carbon, right, this carbon is attached to one carbon, so it's not very big and bulky. Whereas if you go to tert butoxide, so this is called tert butoxide. Okay, this is a huge bulky base. Just look at this thing. You've got the oxygen with the negative charge, but the carbon is attached to 1, 2, 3 carbons, and then you have this base over here, which we won't really see a whole lot of, but that's even bulkier. But what's the trend? Is that as the base gets bulkier, so tert butoxide is what we call a hindered base. It is going to predominantly give you the Hoffman product. Why? Let's think about it. You've got a giant bulky base. Okay, I'll draw the T-butoxide ion like this. Okay, it's got a choice between the blue proton and the black proton. Why does it mostly pick the blue proton when it's that big and bulky? Why does it give you the less stable product in a higher amount? The reason why is because the carbon that has the blue proton on it is only attached to one carbon, where the carbon that has the black proton on it has 2 carbons on it. And so the blue proton is in fact less sterically hindered, so it's easier for this giant base to just pluck that proton off and give you mostly the Hoffman product. So the bottom line is the unhindered base, the reason it can go grab the more hindered proton is because it's going to do it because it's going to give you the most stable product. Okay, so again, to repeat, the bulky base is going to pick the least hindered proton, but that, as a matter of fact, gives you the least stable alkene. But it does it because it's so hindered. When you have an unhindered base, it can pick whichever one it wants, but it's going to give you the Zaitsev product, the more stable product. So that way it's going to pick the more hindered proton. So why does a sterically hindered base favor the Hoffman product? This is what I just explained to you. It's because sterically hindered bases, which we also call non-nucleophilic bases because they can't get to an electrophilic center, they're so hindered that when it comes to your substrate, I'll repeat this one more time. Okay, if you have your substrate like this, they're too bulky to go in and grab, well, I'll put the proton in black. They're too bulky to go in and grab this proton here, but they're able to grab the proton that is attached to the primary carbon. Okay, so what are some other hindered bases besides potassium T-butoxide? This is the one that my students use most of the time. It's called potassium T-butoxide. Amines, so diisopropylamine and triethylamine, these both work well. We have acronyms for those. So for diisopropylamine, I can't remember the acronym at the moment, but for triethylamine, it's TEA, triethylamine. But anyhow, these are all terrible nucleophiles. Why? Because they're too sterically hindered, but they're all good bases. All right. So with that in mind, let's see if we can solve a couple of problems here. So remember, we have to evaluate a few things when we're solving these problems. It says, predict the major and minor products for the following E2 reactions. So they're telling us that these are E2 reactions. So what kind of alkyl halide is this one here? Could anybody answer this? Is this alkyl halide primary, secondary, or tertiary? And it's not a trick question. Exactly, it's a tertiary alkyl halide. Thank you. Okay, so we have a tertiary alkyl halide. If you look, this is the alpha carbon. The alpha carbon is attached to this methyl group, this methylene, I'll put it in black, and then it's also attached to this carbon over here. Now the carbon in green has no protons on it, okay? It has none, 0. So we don't have to consider the carbon in green, But the carbon in blue, okay, the carbon in blue has a beta proton. It's got 3, but I'll just draw in 1 for instructional purposes. And the carbon in black has 2 protons. I'll just put in 1 for instructional purposes only. Okay? And ethoxide, would that be considered, so this is ethoxide here, is that a hindered or an unhindered base? And again, it's not a trick, we're just practicing. So remember, hindered bases are these kind of bases, okay? Hindered bases are big and bulky like T-butoxide, okay? Ethoxide, this is an unhindered base, okay? So it's not hindered whatsoever, okay? So we have an unhindered base. Unhindered base. So when we have an unhindered base, that means that the Zaitsev product, the more substituted alkene, is going to predominate. So let's take a look. If the sodium ethoxide, okay, if my ethoxide ion abstracted the black proton, I'd form the double bond here and lose the chlorine, okay, as a chloride. So let's draw what that would look like. It's going to look like this. Oops. It's going to look like this. So we have the 2 methyl groups over here. We didn't touch those. This one is going to look like this, and we're going to have a double bond here. Okay, that's if it pulled off the black proton. If it pulled off the blue proton, then your curved arrows would look like this. Pull off the blue proton, make your double bond, and lose your chlorine as a chloride. So that would give you this alkene. Like this. Okay, so you have your geminal dimethyl here. Okay, now between the black and the blue, which one is the Zaitsev product? Would it be the black one or the blue one? The Zaitsev product. Remember, Zaitsev is more substituted. It's the black one, exactly. So the black one is the Zaitsev. And so that is going to be our major product. And the Hoffman is going to be our minor product. Now, how do I know that? Because the base is unhindered. So it can pull off either proton, but it's going to pull off the proton, the black proton, because that's a secondary carbon. It's more hindered, okay? This one is going to be, it's going to give you a less substituted alkene. And so since it gives you the more substituted alkene, that's going to be the more thermodynamically stable product. So the unhindered base is going to give us that alkene. Now, if I had had a hindered base, then that's going to give me the less substituted alkene. So let's try it again, okay? If we take a look at this next problem, we have a tertiary alkyl halide. This is our alpha carbon. There are 2 types of beta carbons. There are the ones with the blue protons, and then there's this methylene, which has 2 protons. I'll put those in black. If I have hydroxide, would you consider that a hindered base or an unhindered base? That's an unhindered base, exactly, right? It's an unhindered base, so unhindered. So if it's an unhindered base, I've got 2 possibilities again. I could pull off the black proton, and that would give me this compound. If I pulled off the blue proton, I would end up with, I can do better than that. I'd end up with this compound, which looks like that. Oops, missing a carbon. There we go. Okay, so between the blue and the black, which one is going to be the Zaitsev product? Would it be the black one or the blue one in this case? Which one is the Zaitsev? Which one is more substituted in terms of your alkenes? The black one is the Zaitsev. Great, thanks, Isaac. So this is the Zaitsev. Come on. Okay, the black one is going to be the Zaitsev. And that's going to be your major product because you've got an unhindered base. And the blue one will be the Hoffman. And it is going to be the minor product. Why? Because it's less stable and you have an unhindered base. If you're unsure about the substitution, let's review it one more time. To determine substitution, you look at the two carbons in the double bond. Overall, they are attached to 1, 2, 3 carbons. The other atom is a hydrogen, so it's attached to 3 carbons overall, that double bond. If I look at this one, it's attached to 1, 2. These are hydrogens. So 3 carbons gives you a more stable alkene than 2 carbons. And so the Zaitsev is the more stable product. And so since you have an unhindered base, it's going to give you the Zaitsev product as the major product. In the last one, it's the same substrate again, so it's tertiary. You've got the blue protons and you've got the black protons yet again, but now you have a hindered base, right? T-butoxide is a hindered base, and so in that case, it's going to prefer to give you the Hofmann product. So we're going to get the same products as before. Maybe I'll just circle the whole thing. So you're going to get these same products, so copy and paste those. But now the major and minor are going to be different, right? The Zaitsev will be the minor and the Hofmann will be the major. So this will be our minor product and the Hofmann will be the major because we have a hindered base, right? So a hindered base is going to give you the less substituted alkene, whereas an unhindered base is going to give you the more substituted, which we call the Zaitsev. All right? Give me a thumbs up if you're even like 60% of the way with me on this. Or does anybody have a question about one of these? Why do I get the Hofmann? Why do I get the Zaitsev? Okay, all right. So in terms of stereo selectivity, you guys remember that, if I have trans-2-butene or trans-2-pentene and cis-2-pentene, that these two compounds are stereoisomers. More properly, in this case, these are diastereomers. Diastereomers, okay? Well, it turns out that if you did the elimination here, so we have an unhindered base, right, ethoxide, there's only one type of beta proton anyway, okay? There's these here, but we end up with a mixture of cis and trans. Well, you can see that the trans is more stable, right, because it's less sterically hindered than the cis. So it says use this energy diagram in the Hammond postulate to explain why the trans isomer is formed stereo selectively. Well, it's nothing more than this, that the activation energy, this is not my best work, but the activation energy for the formation of the trans is lower, so it's going to be formed faster. And then if we look at the product, you see the product is closer in energy to the transition state. So anyhow, so we end up with the trans product as our major product, okay? Now, it says here stereospecificity. Watch very carefully, okay? If you're not paying attention, just let me give you 2 seconds. 1, 2, to wake up, okay? So look at these two slides, okay? Look very carefully. These slides said selectivity, selectivity, selectivity. If you go to a buffet, has anybody ever been to a buffet before? I haven't been to one in a long time, but I've been to one before, right? At a buffet, you don't just take one thing, right? You take more than one thing. You're like, I'll get the bacon and the mashed potato. I don't know, right? You get more than one thing, but you're probably selective for one thing over another. That's what selective means. It means you're going to get more than one thing. You get more than one product, but it's selective, meaning you get a major and a minor. Give me a thumbs up if the word selective makes sense to you. Selective means you're going to get more than one thing, like at a buffet, but you're going to get one thing in a greater quantity than another. That's what all this was about. Hofmann and Zaitsev, major and minor, minor and major. It is selective for one over the other. When we talk about stereospecificity, that means that we get one product, okay? Specific, one product, right? Selective means we can get more than one product. We have to predict major and minor. But when something is specific, like let's say you went to a buffet, I don't know why you would do this. You might as well just make it at home. But if you're specific, means you just pick one specific thing, okay? So when we have a reaction that is stereoselective, that means we get a mixture, but we get major and minor. When we have a reaction that is stereospecific, it means we get one product only. So if you take a look at this compound here, okay? Now let me unpack it for you. You see the alpha carbon and there's a halogen. So this is an alkyl halide. if you look at the beta carbons, there's two types. There's this one here that I have the red circle on, and there's this one here I have the blue circle on. If you look at the beta carbon that has the red circle on it, there's no hydrogens attached to that beta carbon. It's only attached to 1, 2, 3 carbons of the methyl groups. But if you look at the beta carbon in blue, that beta carbon in blue has one hydrogen attached to it. Give me a thumbs up if you're with me on what I'm saying. The beta carbon in blue has one hydrogen. The beta carbon, the other one, has no hydrogens. So that means if we want to do an elimination reaction, there is one possibility. Your base is going to take that proton, make a double bond, and lose the bromine. That's it. That's your only possibility. There's no second proton to consider. There's no major and minor. There's just one specific reaction that can happen. And so instead of, can you guys still hear me? Can everybody still hear me? Okay, thanks, Jenny. Good. So as I was saying before the telemarketer interrupted me, is that we're only going to get one product. So instead of getting a mixture of E and Z, you guys remember E and Z? We can't use cis and trans for these products, right? If you look at this one, right, this is going to take priority. So this would be the E product, right? And then this one, this would take priority, this would take priority. This would be the Z product. So instead of getting a mixture of E and Z, we get the E only and no Z in this specific case, okay, with this specific molecule, okay? The reaction is stereo-specific for one and only product, and you don't get any of this. So figuring out whether you get the E or the Z product is interesting, okay? It takes a little bit of work to do that, and I'm going to teach you how to do that right now. So let's take a look at this. It says, to rationalize the stereospecificity of a reaction, take a look at the transition state. In the transition state, the carbon-hydrogen and the carbon-bromine bonds are being broken, and they have to be rotated into the same plane as the pi bond that is forming. In other words, the proton that's being removed, where the pi bond is being formed in the leaving group, they all have to be in the same plane, right? You see how they're all in the same plane? They're all flat. They're not dashes. They're not wedges. They're not coming out. They're not going back. Everything I have on that blue line is in the plane of the screen, okay? They're all in the same plane. If you were to look down, with your eyeball, if you were to look down that carbon-carbon bond, what would you see? Okay, you'd see something that looks like this. Here's your carbon in the back. Here's your carbon in the front. Going down, you'd have that big red proton. In the back, you'd have your bromine up like this. Does everybody see what I'm talking about? So this would be the carbon in the front, and this would be the carbon in the back. Give me a thumbs up if you're with me on that. Cha? Okay. Then, of course, you have the methyl groups. Yes, you'd have a methyl group here and here and here and here. But the idea is if you want your base to pull off this proton, make the pi bond, and lose the leaving group, everything that's involved in the reaction has to be in the same plane. We give it a name. We say it is coplanar. It's all in the same plane like that. We say it has to be coplanar. Now, it turns out that there are two rotamers, two possibilities where we could rotate the molecule where the hydrogen, the two carbons, and the bromine or the leaving group are all coplanar. There's one possibility it's kind of like what I drew on the previous slide where they're staggered. There's another one where they're all eclipsed. Okay, technically in this case, everything is coplanar when everything is eclipsed like this, but that's eclipsed. But eclipsed is really high in energy, and so that's not going to happen. In order for the elimination to occur, it's got to be coplanar and staggered, right? You guys remember that eclipsed is high energy. Okay, that's one way of thinking about it. It says here, since the staggered conformation is so much lower energy than the eclipsed rotamer, we say it only goes, or we discover that it only goes through the lower energy rotamer, okay? So you don't have to worry about drawing any eclipsed Newman projections in this section. Every Newman projection we're going to draw, it's going to be staggered. So now what's going to happen is, remember, the base Okay, the base is going to come along and abstract this proton. You're going to form the pi bond. I can't draw that arrow in the Newman projection, and you're going to lose the leaving group. So you're going to form a double bond between this carbon and the carbon behind it. Now, when you draw the double bond, and here's the double bond right here, you can see on the carbon in the front, you've got the methyl and the phenyl. Okay, good. But what's on the same side of the double bond as the methyl? You see that if the double bond is being formed between these two, that the methyl is on the same side as the tert-butyl, and the phenyl is on the same side as the hydrogen. Okay, so in this particular case, we end up with the E product, right? Because the tert-butyl and the phenyl take precedence. So it's the E product. But so if you're wondering by looking at this, if you're saying, you mean I have to draw the Newman projection and make it so that the hydrogen and the leaving group are coplanar? Yes, you do, okay? But we actually don't use the word coplanar. The reason why is because if it was coplanar, it would mean that the bond or the angle between the hydrogen and the leaving group would be exactly 180 degrees. Okay, that is reserved for coplanar. But when scientists have done measurements of the angles that are used in these E2 reaction mechanisms, it can be anywhere from 175 to 179. So that is not exactly coplanar. That we call anti-periplanar. Okay, so instead of me saying coplanar, from now on I'm going to say the hydrogen that's being abstracted and the leaving group have to be anti-periplanar to each other, right? They can have a slight deviation from being coplanar. Now, another thing is sometimes students will say, well, am I mostly going to get the E isomer? Because that's usually more stable. There's no way to predict, man. You can't do that. You can't make a prediction. You have to draw the Newman projection and figure out which product you're getting, because oftentimes you're going to get the less stable isomer. It happens all the time. Okay, so there's no shortcut around it. You always have to go through the Newman projection. So it says here, assuming they proceed through an anti-periplanar transition state, predict the products for the following reaction. So we would have our base. Okay, let me put my lone pairs on my base. Okay, the base is going to grab the proton, right, and make the double bond like that. Well, what are we going to get? Are the two R groups in red? Are they going to be on the same side of the double bond or opposite sides? Now, I'm sure you can answer that without my help, but I'll show you the proper way to do it, which would be to look down the carbon-carbon bond and make a Newman projection so that the proton, right, the hydrogen, and the bromine are anti-periplanar. And you can see that on the carbon in the front, I have the red R1, and then the carbon in the back, I have the red R1 coming over here. I have the R2 coming over here and the R2 coming over here. So it's pretty clear that the two red R1s are going to be on the same side of the double bond. So after I do the elimination, okay, I'm going to end up with something that looks like this. We're on one carbon. I'm going to have R1 and R1, and on the other one, I'm going to have R2 and R2. Give me a thumbs up if you're part of the way with me on that. Or does anybody have a question about that Newman projection? Everybody follow me on drawing a Newman projection. Anybody? No? Okay. Well, stop me if you have a question, okay? Because we're going to take a look at a specific example here in just a second, okay? Now, if you do the same thing for the next one, so if you do the same thing for the next one, what you're going to see is you're going to end up with your double bond, and you're going to have your R1 that are going to be trans to each other, and then your R2s are going to be trans to each other, like that. Sorry about that. All right. So stereospecificity of E2 when you have two beta substituents. So the only time it's going to be stereoselective, okay? So if it's stereoselective when you have one beta proton. If you have two beta protons, you don't have to draw a Newman projection. So here we have two beta protons. In that case, you just draw both of the products, and whichever one is less sterically hindered, we usually say that one is going to be the major product. So sometimes students will ask me for summaries of something, okay? So let's take a look. There's a difference between stereoselective and stereospecific, okay? In stereoselective, we have more than one beta proton, okay? So in that case, we're going to get a major and a minor product. That is selective, okay? If it's stereospecific, in that case, it means you have one beta proton. Let's put one beta proton only, okay? And so it's only going to give you one product, right? So in this case, okay, one beta proton only. For these ones, you have to draw Newman projection. Whereas when it's stereoselective, you don't have to draw the Newman projection. You just look at the major and minor products. Whichever one is less sterically hindered, that's going to be the major product. So we'll put here less hindered, okay? Will generally speaking be the major product. Okay, so let's take a look at these two reactions. It says identify the major and minor products for the E2 reaction that occurs when each of the following substrates is treated with a strong base. So I'm just going to put a generic base. It doesn't matter. It could be ethoxide or something. You know what? Let's use ethoxide. It's a strong base. Okay, I'll leave out the sodium because that's a spectator ion. But there's my strong base. Here is my alpha carbon. This is a beta carbon, the one in blue, and this is a beta carbon, the one in the black. The beta carbon in blue, does it have any hydrogens attached to it? Are there any hydrogens on the blue one, the blue carbon, or the carbon with the blue beta next to it? Are there any hydrogens? None. Zero. Nothing. Okay? So we can forget this one. Okay, next question. If I highlight this carbon in black, how many hydrogens are attached to that carbon? That beta carbon? 2. Thanks, you guys. So that means I've got a proton coming out, and I got a proton like this, okay? So that means this reaction is going to be stereoselective. Okay, so that means I'm going to get a major and minor product. So my base is going to pull off, and I could draw it to either one of the protons. It doesn't matter. I'm going to form the double bond and lose my leaving group. So that means I'm going to get 2 different alkenes. Okay, I'm going to get 2 different alkenes. I'm going to put in the aromatic ring. I'm just going to put pH for aromatic ring. Okay, because this black carbon only has an aromatic ring and a proton. So we'll put a proton and a proton. Okay, like that. On the other carbon, I have a hydrogen, which isn't shown. Okay, this one here, and I've got a tert-butyl group. So I've got 2 possibilities. I've got one where the tert-butyl group is on the opposite side of the phenyl, and then I've got one where the tert-butyl group is on the same side of the phenyl. Okay, so you see that this compound, the one on the left, you see the 2 protons are trans, so you could call it a trans compound, or you could see that these 2 groups are E, so we could call this trans or E. Either one is fine. And then this one would be cis or Z. Okay, so there you go. Based off of your intuition, which one of these do you think is going to be the major product? Would it be the trans or the cis? And we've talked about this already, and it's not a trick. It's yeah, exactly. Thank you. Thanks, Isaac. It's the trans, right? So this will be the major product, right? We didn't have to draw a Newman projection. Why? Because this reaction is not stereospecific, it's stereoselective. Okay? So there you go. So that's what you have to do with these, is just draw both products and just figure out which one is less sterically hindered. It's going to be your major product. Hot dog, we have a wiener. You're done. Okay? So now let's take a look at the next one. Okay, next one is trickier. I'll admit it. We have an alpha carbon here. This carbon has no hydrogens attached to it. But this carbon here in blue, how many hydrogens are there attached to that carbon in blue? And it's not a trick. Thank you, Isaac. There's 1 measly proton attached to this. Okay? So we have the hydrogen in the bromine that are going to be involved in the reaction, right? You could even say, oh, I'm going to take my ethoxide. I'm going to draw my curved arrows. There's nothing wrong with that. I would, you draw, make your double bond, lose your leaving group. Great, okay. But the question is, do you get the E product or the Z product? Okay, this reaction, since there's only one beta proton, this is going to be stereo specific. We're only going to get one product. And the way that this is drawn, you can see that the bromine and the proton are not coplanar, right? They're not drawn anti-periplanar to each other. They're both pointing into the page. And so what we're going to do is this. We're going to go right back to, which was it? Which chapter did we cover the Newman projections? They start to get mixed up in my mind sometimes. So we're going to look down this carbon-carbon bond, and we're going to draw the Newman projection. So I'm going to do it a little quicker now. But we've got the carbon in front, which is going to have the phenyl. We've got the carbon in back. Okay, the carbon in back is going to have the tert-butyl group coming down like this. The carbon in the front is going to have the proton going down to the left like this. It's going to have the methyl group going down to the, I guess I'll just redraw all that, get some more practice. Okay, let's go back. Let's go back here. Hey, not that bad, actually. Okay, didn't lose that much. So where was I? Just give me 1 second here. All right. So we have our ethoxide ion. Okay, so let's practice drawing our Newman projection again. Okay, so we've got our eyeball. We said we're looking down this carbon-carbon bond. So here we go. So we've got the carbon in the back, got the carbon in the front. The carbon in the front has the phenyl, like this. In the back, we've got the tert-butyl going straight down, like that. The carbon in the front has the methyl group over here. It's got the proton over here. In the back, we've got the bromine on the same side as the proton. And then we also have a hydrogen over here. So what we have to do is we have to put this bromine, the leaving group, and this hydrogen on the carbon in the front. We have to put those coplanar to one another. So there's a number of ways you could do it. You could rotate the bromine back here. The way I'm going to do it is I'm going to move the proton over here. I'm going to move the methyl group up here, and I'm going to put the phenyl group down here. Okay, so I'm going to rotate 120 degrees. So I'm going to rotate 120 degrees. And then what I'm going to end up with is this. So the carbon in the back doesn't change at all. Okay, I still have the bromine here. I still have the hydrogen here. I still have my tert-butyl group down here. And then I have something going straight up. There's something going over here. I have something going over here. Okay, so now I'm going to rotate it again. So I'm going to rotate it in counterclockwise fashion. So the hydrogen will be over here. The methyl group will be up here, and I'll put the phenyl down here. Does it give me a thumbs up if you see what I just did by rotating that? I took up way too much space doing it, but anyhow, you get my drift. Okay, so now,
Mr. John,
yeah, go ahead.
how did you know that that one was stereo specific again?
Okay, so when it's stereo specific, okay, if it's stereo specific, you have one beta proton only. Okay, so if we go back here, okay, here's our alpha carbon. This is a beta carbon, the one that I have highlighted in yellow that doesn't say alpha. There's no hydrogens on that. This is also a beta carbon, and there is one hydrogen. So if there's one beta proton, the reaction will be stereospecific.
And because there was one beta proton that just had a hydrogen on it?
No, one beta carbon that has one hydrogen. Hydrogen and a proton mean the same thing.
Got it. Okay.
Okay, hydrogen is the same thing as saying a proton. All right, so this is a beta carbon. This is a beta carbon. This beta carbon has no hydrogens attached. This is a carbon, 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 carbon. The beta proton on the left, right, this one here is attached to carbon, 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 but it's got one hydrogen attached to it. So that means the reaction will be stereospecific. Okay?
Okay.
Does that help?
Yes, that makes sense. Thank you.
Yeah, no problem. So now you see that the bromine and the hydrogen are anti-periplanar. Son of a gun. But they are anti-periplanar. So now when I form the double bond, you can see that I've got the methyl group and the phenyl are going to be on one carbon. So I'm just going to draw the product of the elimination down here. So I've got my double bond. It's going to have a methyl group on it on one carbon and a phenyl. Okay. But what's on the same side as the phenyl? Well, you can see it's the tert-butyl group, right? So the tert-butyl group is on the exact same side as the phenyl. And then you see that the hydrogen is on the same side as the methyl, like that. So that's going to be the major product. It's going to be the only product of the reaction. And so how would you label this product? Would you call that an E product or a Z product? What's in that box? Would that be an E product? I can fix this, okay? But is that an E product or a Z product? It's a Z product, isn't it? Okay, thanks, Isaac. It's the Z product, and that is the only product of the reaction. All right, only one product. There's nothing else formed. So if you're like, I like these reactions, only one product. Yes, but we usually ask you a question where you will have to draw a Newman projection like this, and you'll have to adjust it so the leaving group and the proton being abstracted are anti-periplanar to one another. All right, so stereospecificity of an E2. So continuing on with this idea, we can actually see this also manifest when we look at cyclohexanes that contain a good leaving group. So this is just chlorocyclohexane. This molecule, it's the same molecule. This is chlorocyclohexane. That's right? It's the same molecule, okay? But you see that here it's axial, here it's axial, here it's equatorial, and here it's equatorial. Well, the thing is if you want to do an E2 elimination reaction with a leaving group on a cyclohexane, it has to be in the axial position. Okay, it can't be in the equatorial position, and you can see why, because when it's in the axial position, you can have a proton that is going to be anti-periplanar to it, whereas when it's equatorial, it's a methylene, right? This is a carbon. This is a CH2 group. It's not a proton. So this will not work in an elimination. The only way it's going to work in an elimination is if your leaving group is axial, because then again, you have protons that are anti-periplanar to it, okay? But when it's equatorial, doesn't work, okay? So if you take a look at these two molecules, it says here, which of the two molecules below will not undergo an E2 elimination? Remember, in order for an E2 elimination to occur on a cyclohexane, the leaving group has to be axial, and the proton being abstracted has to be axial. Okay, so let's look at this molecule here. If this chlorine, if we imagine this chlorine as being up, if we imagine this chlorine as being up, which it is, because it's on a wedge, right? You would all agree with me on that. If we imagine that it's up and axial, then we have fulfilled the requirement for it to be a leaving group, right? Because I just told you the leaving group has to be axial on a cyclohexane. So this is our alpha carbon, this is a beta carbon, and this is a beta carbon. Both of the beta carbons have protons. Good. However, you're not going to get any reaction here. There's going to be no elimination. Why? Because this proton is up, but is that proton up and axial? Could anybody answer that? Is that proton up and axial? First of all, it would have to be down, but no, it's not axial because axial and equatorial alternate. So this chlorine is up and axial, but the proton is up and equatorial, and this proton is also up and equatorial. So there's going to be no reaction here whatsoever. However, if I look at this and I say my chlorine is up and axial, then this proton is down and what? Could anybody answer that? If the chlorine is up and axial, that means that the neighboring, exactly, is down and axial. And that means that this proton is down and axial. So that means in this case, we will get a reaction. We can have an elimination. Somebody doesn't like me up there. I think God is trying to tell us something that maybe class should be over soon. But the idea is, again, if this is up and axial, this proton is down and axial. And so we could get an elimination here to form cyclohexene. Whereas here you'd have no reaction in that specific case. So you can see that manifest here, okay? It says here the E2 reaction is slow, but you only form one product. Why? Let's take a look. If this chlorine, right, is down, and axial, that means that this tert-butyl group is up and axial, and it would mean that this proton here is going to be up and axial. So the elimination reaction is going to occur between the leaving group that is down and axial and the proton that is up and axial. It can't occur with this proton here, right? Nothing's going to happen with this proton because it's down and equatorial. So that one's not going to be involved in a reaction. But why is this reaction so slow? The reason it's so slow is because when it's in the chair form, you have to have this giant tert-butyl group in the axial position. That's not good, right? You'd have to have something that looks like this, where you have this giant tert-butyl group in the axial position. The chlorine is in the axial position, and the proton. So yes, you can form or do the elimination between this proton and the chlorine, but now you've got all these 1,3 diaxial interactions with the tert-butyl group, right? You don't want to have a tert-butyl group in the axial position. It's really unstable. Whereas here, the reaction is going to be really fast. Why? Because if the chlorine is up and axial, and this hydrogen is down and axial, we fulfilled the requirement for an E2 elimination, but this hydrogen is going to be down and axial, which means that the tert-butyl group is going to be up and equatorial, and that's not that bad, okay? Having a tert-butyl group in the equatorial position is going to be more favored. And so we're going to get a mixture of products in this case, right? The elimination can occur between the chlorine of this proton or this proton, right? So in that case, we would get a mixture. So when we're drawing products of E2 reactions, what's our conclusion? There's many things that we have to consider. Cause legion, for we are many, right? Anyhow, you have to consider, is the reaction going to be stereospecific? If it's stereospecific, you've got one beta proton, and therefore you get one product. Okay? If the reaction is stereoselective, you've got at least two beta protons, and that means you're going to get more than one product. So I'll put products here. So are you going to get regioisomers? Are you going to get the Zaitsev? So if it's regioisomers, are you going to get the Zaitsev and the Hoffman, right? Are you going to get those? Are you going to get the E or the Z if it's stereospecific, right? Those are the kind of things we have to consider. And so these are the words of the author of the textbook. So if you say, I don't like Mr. Dion, I don't like his style. Well, you can take this from Dr. David Klein, PhD, author of our textbook, amazing organic chemistry teacher, okay? I've spoken to him a couple times. Anyhow, he says the only way to master this material is to do lots of practice problems, okay? You've got to do lots of practice, all right? A lot of practice to master it. So what we're going to do then is before class on, what's today, Tuesday? So before class on Thursday, so on June 6th, 6624, we are going to start by taking a look at these problems here. And here we have unhindered bases, and you have to determine whether these reactions are going to be stereospecific or stereoselective, and then figure out if it's selective, figure out what the major and minor products are, okay? I'll give you a clue. Both of these are stereoselective, so you're going to end up with major and minor products in both of these specific cases. But I think that would be a good place to start. And by the time you're finished doing a bunch of practice, you'll probably be able to solve these pretty quickly.